And okay. Share screen. Just give me a moment. I'll share the screen. I mean, share the iPad screen. It is. Come on. My iPad is not recognizing the internet yet. Okay, let's see. Okay, finally. Good. Okay, so now you can see the white screen, right? Okay, so we were doing this initial value problem, and what I'm going to do is, so what I'll do is to show you a prototypical problem of differential equation, and then move on to eigenvalue, move on to diagonalization. Let's start on the new page. So solve the, what's going on? So this is a typical example of initial value problem. So y1 prime equals 2y1 minus 6y3. y2 prime is y1 minus 3y3. And y3 prime is y2 minus 2y3. So recall that this yi prime, this is dyi dt. And we also have this initial condition that y10 is y10 equals y20 equals y30 equals 2. Okay, so this is the initial condition. Okay, so let's set up the problem, and the part about solving the eigenvalues and eigenvectors I will do it quickly, but let's first set up this problem. So how does it look like? You have y1 prime, y2 prime, and y3 prime. Okay. Now this is the matrix A, so 2, 0, minus 6, the usual way that you find the coefficient matrix. So this is very similar to system of equations, linear system of equations. Just remember that you are dealing with differential equations instead of linear equations. Okay, so this is the matrix vector form here. So this is my coefficient matrix. Okay, so then let's see. Okay. Then, so what do we need to do? We need to, in order to find the solution, we need to find the eigenvalues of this matrix A. So find eigenvalues and corresponding eigenvectors of A. So this part is, for the moment, it's well known. We have found enough eigenvalues and eigenvectors for matrices. So still, let's write down at least the polynomials. So P lambda, so this is the determinant of A minus lambda I3 in this case. So this is 2 minus lambda, 0 minus 6, 1 minus lambda, minus 3, then 0, 1, and minus 2 minus lambda. Okay. Oops. Okay, so this equals 0. So this is our equation. And solving the determinant part, I will leave it to you. So this will give us lambda times lambda square minus 1. So this equals 0. Okay, you can do it in any way you like, just solving it using the first column or maybe the first row, whichever way you like. Then, okay, so this is the equation. So the eigenvalues are what? So lambda 1 equals 0, corresponding to this factor. Then lambda 2 equals 1, corresponding to 1 root. And then lambda 3 equals minus 1. So these are the three eigenvalues of the matrix, the three roots, you can say. Then, okay, so we have found the eigenvalues, then the corresponding eigenspaces. So corresponding eigenspaces. Okay, so the first thing is, let's see, E of 0. So E of 0 is just the null space of A. So there's nothing much to do. You have 2, 0, minus 6, 1, 0, minus 3, and 0, 1, minus 2. So this is the matrix A. So you can reduce this to 1, 0, minus 3, then 0, 1, minus 2, then 0, 0, 0. So finally, what you have is the following. So E0 is given by the following vectors. X1 has to be 3x3 and X2 has to be 2x3. Okay, so this is span of the following vector, 3, 2, and 1. So you replace x1 by 3x3 and x2 by 2x3. So you get this vector which generates the null space of A. Okay, so then let's see. So this is the null space of 0 now, or rather the eigenspace to 0. Then eigenspace to 1. So this is null space of A minus just I3. Okay. So I'll just give you the final answer. So this is span of 6, 3, and 1. So this complete this part. Similarly, E of minus 1. This would be null space of A plus I3. Okay, so once again, this is span of, let's see. Once again, this I leave you to complete. I mean, these are just exercises in finding null spaces, so it's nothing new. Now, once you have done this, so you have these three vectors, or these three eigenvectors, which span the null space, span the eigenspaces corresponding to 0, 1, and minus 1, namely 3, 2, 1, then 6, 3, 1, and 2, 1, 1. So any other eigenvector for 0, let's say, they are either linear spans of 3, 2, 1, or for eigenvalue 1, it's linear span of 6, 3, 1, or multiple of 6, 3, 1. For minus 1, it's the multiple of 2, 1, 1. Okay. So these are the representative eigenvectors from the eigenspace. Okay, so now the general solution of the differential equation is given by, let's use, since we are using y1, y2, y3, let's use the vector y. So y equals alpha times, so 3, 2, 1 was the first one, 3, 2, 1 is exactly, so 3, 2, 1. So this is the eigenvector corresponding to eigenvalue 0. Now e to the 0t. So remember, e to the eigenvalue times the variable t. Okay, so e to the 0t plus beta times, so alpha, beta, and there will be one more. So 631 e to the t corresponding to the eigenvalue 1 plus gamma, plus gamma times 211 e to the minus t for scalars alpha, beta, and gamma. So this is the general solution. Okay, so is this clear how I went about? So if you look at the lecture notes, you will see exactly this is what's going on. We find eigenvectors and eigenvalues corresponding to the matrix A, and then find the general solution by adding each solution, let's say. So alpha times 321 e to the 0t, this is one solution. Beta times 631 e to the t, another, and the third one is gamma times 211 times e to the minus t. And then we add this up with the scalars alpha, beta, and gamma. So different values of alpha, beta, and gamma will give you different solutions. Okay, so then let's write it down in terms of a vector. So y is given by, so e to the 0 is simply 1. So 3 alpha plus 6 beta e to the t plus 2 gamma e to the minus t. Then 2 alpha plus 3 beta e to the t plus gamma e to the minus t. And the last row is alpha plus beta e to the t plus gamma e to the minus t. So this is the general solutions for different values of alpha, beta, and gamma. Now, to find a particular solution, what we need are the initial conditions. Okay, so the initial conditions are given by this constraints that y1, y2, and y3 at t equals 0 is just this number 2. Okay, so the initial condition gives particular solution for alpha, beta, and gamma. So we'll have three linear equations basically. So y 0, so this is simply y1 0, y2 0, y3 0. This is given by, on the right hand side, you plug in t equals 0. So this is 3 alpha plus 6 beta plus 2 gamma. So remember that t equals 0 here. Then 2 alpha plus 3 beta plus gamma. Then alpha plus beta plus gamma. Now you see what's going on. You have three equations and three unknowns. So we have 3 alpha plus 6 beta plus 2 gamma equals 2. Then 2 alpha plus 3 beta plus gamma equals 2. Then alpha plus beta plus gamma equals 2. So these are three equations in three unknowns. Okay, so now you solve them. So we solve to get, I'll just leave it here to get a particular solution. Okay, so this is a prototypical example. Any problem in eigenvalue, rather in differential equation involving eigenvalues and eigenvectors would be of this type. So we'll be given a linear system of equations, a linear system of differential equations. Typically, you will find the eigenvalues and eigenvectors, and then either you'll be asked for the general solution or you'll be asked for the particular solution. Okay, so that's it. So I leave it here, leave you to solve for alpha, beta, and gamma. So any questions here? This is just following the methodology, nothing else.
You set it equal to 2 by just picking a random number.
Just give me a second. Once more.
You set all three equations equal to 2. Was that just like a random number you picked?
That's the initial condition. It could be 2, it could be 3, it could be half, it could be anything. So that's the initial constraint, you could say. So at t equals 0, y1, y2, and y3, all three of them have the value 2. So this 2, you can say that like 2 units, something like, I don't know, 2 kilometers, you could say, depending on what problem you're solving. It was, yeah, exactly. So it was given in the problem, this initial condition. Okay, so that's that. So let's move on to the next topic. Begin on the next page. So this is, we are now moving on to note 10. So this is note 10, eigen 3. Okay, so this is called diagonalization. So what is the essence of diagonalization? The point is that if a matrix is diagonal, then that's perhaps the easiest form that you can have. So diagonal matrices are easy to multiply. So multiplying two diagonal matrices is basically multiplying numbers. So you multiply elements in the diagonal. So the multiplication is extremely simple. Then, I mean, doing almost anything with diagonal matrices is doing things with real numbers, let's say. So there's nothing much different. So diagonal matrices are probably the easiest matrices to work with. Now, unfortunately, not every matrix is diagonal. So there can be complicated matrices which are not diagonal. I mean, of course, there are many examples of that. So diagonalization, it measures how far a matrix is from being diagonal. So that's like a vague idea that we measure how far it is. So what are the conditions needed so that the matrix can be diagonalized? So let's be a bit more formal. Okay, so this is the topic. Maybe I will write it here. So diagonalization. So a little bit of it will involve some definitions and theoretical parts. So we have to be a little bit patient, and then we will move on to examples. Okay, so definitions. So two matrices, A and B, are said to be similar if there exists an invertible matrix P such that B equals P inverse A times P. Okay, so somehow B and A are related through this invertible matrix P. So then we call A and B to be similar matrices. Now this is an easy problem and we will solve it completely. So similar matrices so they have the same eigenvalues. So that's the crucial point. So if you know that two matrices are similar and one matrix is simple enough to work with, then knowing the eigenvalue of that matrix gives you the eigenvalue of the other matrix. So you don't need to do separate computations. So let's see why that is true. Okay, so A and B similar means that there is a P such that the definitions of B is P inverse AP. Okay. Now, what is the polynomial equation corresponding to B? So the polynomial equation so let's give it a name, PB of lambda. So this is the determinant of B minus lambda IN. Okay, so this is the polynomial equation which computes the eigenvalues. Okay, Now replace B, of course, by this equation. So this is P inverse AP minus lambda IN. Okay. Now it's just a matter of placing these invertible matrices in the correct order. So lambda, so we could rewrite this identity as P identity times, or rather P inverse identity times P. Okay, because P inverse times P is identity. So now we can take out P inverse from the left and P from the right. So we can rewrite this as P inverse times, let's do this slowly, A minus lambda IN times P. So do you agree with this step? So this is the crucial step here. So this is so we take out P inverse from the left of both the equations and P from the right. Agree to that, or any questions? Okay, I think it's fine. So now you know that in the realm of determinants, we have more freedom. So this is P inverse times the determinant of P inverse times the determinant of A minus lambda IN times the determinant of P, but these are real numbers, so you can write it as P inverse times P times this A minus lambda IN, but this is simply the determinant of identity, which is 1. So finally what we get is just the determinant of A minus lambda IN, which is nothing but the polynomial equation corresponding to A. Okay, so what we get finally is that the polynomial equation corresponding to B is same as the polynomial equation corresponding to A. And of course then, so PB lambda equals PA lambda. Hence, the roots and, well, let's write just the eigenvalues. And hence the eigenvalues of A and B must be same. Okay, so they have exactly the same eigenvalues because the equations are same. Now that's a good thing about similar matrices. Now this is the fundamental problem which I was talking about. So given a matrix B, or rather given a matrix A, can you find an invertible matrix P and a diagonal matrix, let's say D, such that A and D are similar through this invertible matrix P? So that's what we call diagonalizable. So this is the next definition. It's a square, always square. Matrix A is called diagonalizable if it is similar to a diagonal matrix D. So D has to be of this form. So A1, AN. So it's a diagonal matrix. So A has to be similar to a diagonal matrix. So there exists, so there should be an invertible matrix P such that D equals P inverse A times P. Okay, so that's what is called a diagonalizable matrix. And the process of getting a matrix P and the diagonal matrix D is called diagonalization. So this is the process of diagonalization. Okay, so now the next inevitable question is the following. Right, so we know that not every matrix is diagonal. Of course, there are plenty of examples, but we can ask whether all matrices are diagonalizable. So whether there exists this invertible matrix P and a diagonal matrix D such that we can write A and D, or we can relate A and D through this matrix P. Okay, so that's a natural question. I mean, what may happen if all matrices are diagonalizable, or what is the good thing is that then we do not need to worry about computing eigenvalues of any matrix, or I mean, we can be perfectly happy with eigenvalues of a diagonal matrix, and eigenvalues of diagonal matrices are just the diagonal elements. So even this problem of finding eigenvalues and eigenvectors of a matrix would become much easier if we know that every matrix is diagonalizable. Okay. And as with all this grand wishes, this is not true. Okay, so not all matrices are diagonalizable. So let's look at a counterexample. Okay, let's take A to be the following matrix, 0, 1, 0. So this will involve slightly logical argument. So you have to, it's completely a logical, let's say, logical deduction. We will show that A is not diagonalizable. Firstly, A is not diagonal. That's quite evident because there are entries in the position A1, 2 and A2, 3. Okay, so it's not diagonal. Now, how does one show that this cannot be diagonalizable? What we do is, so we show that A is not diagonalizable through what is called reductio ad absurdum. So something like there is a statement. So we have done arguments like this, that there is something which is universally true, and we will show that if A is diagonalizable, then that universal truth is not valid. So then A shouldn't be diagonalizable. So that is the point. Okay, so let's say, so let A be diagonalizable. So what does it mean? There exists a diagonal matrix D. Let's write it down. So this is A1, A2, A3, and zeros everywhere else. And an invertible matrix, questions, and an invertible matrix P such that D equals, this is the definition, P inverse AP. Okay, so this is being diagonalizable. Now here is the property of A which we want to use. So check that A cube is the zero matrix. Okay, so if you multiply A thrice, then it will give you the zero matrix. Now, A is given by, of course, P, D, P inverse. Okay. Rather, let's this is not needed. Okay, now let's try to find out what is D cube. So first, what is D square? So D square is D times D. So this is P inverse AP times P inverse AP. Okay. Now, matrix multiplication being associative, you can rearrange the brackets. So this is P inverse A, P inverse AP. Okay, so agree. So I place the brackets around P and P inverse. But this is simply identity. So this is just P inverse A times identity times A times P. Or in other words, this is P inverse A square times P. Now D cube is, once again, this is P inverse A square P times P inverse AP. And exactly following this methodology, what you get is this is P inverse A cube times P. Okay, so it's exactly the same method. So P times P inverse would be identity. So you'll be left with P inverse A square times A times P. So it's P inverse A cube P. But you know that A cube is zero. Okay, so then this is simply P inverse times the zero matrix times P, or it's the zero matrix. Okay, so what we get is that if A is diagonalizable, there is this matrix D, which is diagonal, and also satisfies this property that D cube is the zero matrix. Now, what does this mean? Can you guess what's going on here? Remember that D is a diagonal matrix. So what does D cube equals the zero matrix actually mean? Any ideas?
Zero matrix?
What's that?
Is it the zero matrix?
You mean D is the zero matrix?
Yes.
Exactly, yeah, exactly. So let's elaborate on what he's saying. So D cube is given by A1 cube times A2 cube times, not times, sorry, A3 cube. So you simply multiply the elements in the diagonal. That's it. So this being the zero matrix, it simply means that A1 cube, A2 cube, and A3 cube, all of them are zeros, which means that A1, A2, and A3 are zeros. Okay, so that's that. So D is simply the zero matrix. But that's a problem, right? So if D is a zero matrix, then what do we have? We have from this particular equation, so D is equal to P inverse AP, what we have is that the zero matrix equals P inverse AP. Or in other words, A is P times the zero matrix times P inverse. So it's the zero matrix. So from this assumption that A is diagonalizable, we arrived at this impossible conclusion that A has to be the zero matrix. But evidently, I mean, A is given. A is a non-zero matrix, so A cannot be. So, but A is certainly non-zero, right? So the assumption that A is diagonalizable must be wrong. Hence, A is not diagonalizable. Okay, so this is what the point is, that A is not zero. That's a universal truth. I mean, A is right in front of you. It's a non-zero matrix. The assumption that A is diagonalizable, that's where the problem is. If we assume that A is diagonalizable, we arrive at some conclusion which contradicts this universal truth that A is non-zero. So this assumption that A is diagonalizable has to be wrong, and hence it's not diagonalizable. So this is one of the very few sort of proofs of this type that we will see. Maybe this is the only one, I don't know. So any questions about it? Is it absolutely clear why this is? So is that why there is a requirement that it needs to be invertible? You mean the matrix P? Yes, I mean, in the condition of similar matrices, this condition is imposed in the definition of similar matrices, that this matrix P has to be invertible. Otherwise, I mean, you cannot write B as P inverse A times P. If there is no inverse, then you cannot do that. So this condition of invertibility of P is imposed on the definition. And you are using that in this particular problem, in this particular example, that A is not diagonalizable. Precisely here, that P times P inverse is identity. So that's where you're using it. Okay, so I think that's a good point to stop. So what I do in the next class is carry on with characterizing diagonalization and solve a few problems. So I want to finish off with this diagonalization by next week at least, so that we can have some time for the vector calculus. Okay, so any questions from your part?
How do you want us to turn the test in once we've taken it?
Yeah, you can do that. Yeah, I mean, the time limit is till Thursday.
No, I mean, like, you know, we wrote it on paper, right? How do you want us to turn it in?
Yeah, so that's the point. So as one of you were saying that I can set up a submission box on eCampus, so I'll do that, and once I do that, I'll let you know. So you can put your, so you can scan your exam, or you can write it on your iPad and save it as PDF and upload it on the submission box.
Sounds good.
Okay, so I'll let you know, or else that would be like the worst possible scenario is that you send me the copies through email and I will keep track. Send the PDF version through email. So that will be a bit time consuming, but anyway, I'll keep track of your submission. But whatever be it, I will let you know by Thursday or at most Friday. Okay. Okay, so anything else that you want to know, or else we will end this session here and I'll be back at 4. What time is it due? It's written on the exam. It's due on Thursday, 2:30. So you have like 2 days to finish it off. Yeah, as I said, I mean, if you want to take it exactly as a test, then keep an hour and 15 minutes and just finish it off at the time. And I mean, that's up to you, and you have to be your own proctor, I guess. Or you can ask your dog to be your proctor. Anything else for now? Okay, so then I will stop this lecture here and I will be back at 4. Okay, bye. See you on Thursday then.